read from my email address. I'm currently working in France, Paris, on the NMR techniques. And so the title, the GIPAW NMR, I will explain the acronyms during the talk. But basically what I concentrate in this talk is the method, the implementation of the NMR spectroscopy, what's included in the quantum espresso package. So I'm not going to spend the whole talk discussing NMR in general, but I will try to explain in the beginning, the introduction, how to go, or how the experiment gives the physics, which is then incorporated in the theory. The outline is, so first there's the introduction to NMR, the main techniques which I will be talking about, the experimental observables, they're the so-called chemical shielding, CS, and electric field gradients, EFG. Then I discuss this method, like I mentioned, so that's the way how to calculate those observables, chemical shielding. Then PAW, which was introduced, I think, last week for the electric field gradients. And then third, I will show examples of applications that have been calculated using the GIPAW method. Actually, most of them using other codes. But now that the GIPAW is working in quantum espresso, one can use it also. And then shortly, I will describe some details about using the GIPAW module in quantum espresso, some aspects of it. So I start with a short introduction to NMR. So for those of you who don't know, the NMR is nuclear magnetic resonance. So one is looking at magnetic properties in this case, and this is a spectroscopic method. So one gets microscopic information and really at the atomic scale, and it's sensitive to the local environment around the atoms, but it's not, say, a real space method where you could directly see and get direct signals. So it needs some modeling or theoretical input, at least empirical rules. So if you see a signal, what does it mean in the terms of the local environment around the atoms? But of course, this theoretical input and modeling, that's what we are here for, so we can really be useful for the experimentalist, where you can do solids, and this is of course what quantum espresso is best for, the solids, amorphous, liquid samples, and then the gaseous one, I mean, it's more efficient probably using localized bases. Well, I just mentioned the time scale is milliseconds, so you cannot really follow chemical reactions as they happen, and, so you need some averaging of milliseconds. So the principle of magnetic interaction, if you have a magnetic dipole and then you put on a magnetic field, on this axis there's the strength of the magnetic field, so you get the splitting because the magnetic field interacts with the spin, and this energy depends linearly on the strength of the magnetic field. So if you have an external magnetic field, in this case it's shown as a homogeneous magnetic field, then you get the induced magnetic field, and that's the total magnetic field inside the sample. And this magnetic field, so in this example, you see the magnetic field in this direction, it induces some ring currents. So if you remember from the electrostatics actual equations, so you will get currents in the magnetic field. And well, here yes, again the picture, this is, say, the newest generation NMR equipment. So the 1000 stands for 1000 megahertz, and that's really the latest art, or the latest what they achieve in equipment. And so if you have here again the magnetic field, and then you measure this distance, so you get the resonance at that energy. So if you have this distance. So usually what one does, one has two magnetic fields, one static homogeneous field which aligns the spins in one direction, and then one has an oscillating field which oscillates between these two energies, or these two levels. And so from the second one, this oscillating field, you get this peak a function of, well, the frequency in that case. And as we mentioned, the method is sensitive to the local chemical environment, and this is just an example. This is now already the observable called chemical shift, and it's measured using ppm, so it's a part per million, so it's a very small number, but you see that well, these are examples for hydrogen, and you see different groups where the hydrogen is chemically bond, and then you have these characteristic regions in this observable for different chemical local environments. So if you get the signal around this well, chemical shift, you know that it's probably the hydrogen is probably bound in this kind of chemical group. So in this way, you get the signal. Well, sometimes you might have two possibilities, but using this, you can derive what is the local environment of the hydrogen in this case. And so it's like shown in the beginning, so it's nuclear technique. So one needs a nuclear dipole to induce the NMR signal. And here, which are shown in nuclear, which have a spin 1/2. This is the nuclear spin. And the red ones are those which have this nuclear spin 1/2. The bottom hydrogen you can use for these techniques, and the carbon nitrogen. So biological samples, one can use this for already for the dipole, so or dipole line interactions. Then one has higher nuclear magnetic moments even here in different colors, and you see that you cover almost the whole periodic table. And also this you can use either for the chemical shielding, or when the I is bigger than 1, you can use also the electric field gradients. So you see that there are plenty of elements that you can use, but usually these are only some isotopes, so it's not necessarily the most abundant or most abundant species in nature. For example, the carbon, which I showed the previous slide, this one, so this carbon-13, and it's around 1% in abundant in nature. So sometimes the signal is too weak, because you have only 1% of the carbon in the sample. It's the active one for NMR, so one has to use the isotopic enriching. So one inserts, when one prepares the material, one inserts more of the isotope, which is active, it has a nuclear moment. Well, then coming towards the theory, so this is the NMR Hamiltonian, and I will go through those terms which we will need today. So if we start here, we have the nuclear spin, is the I, you see it's here, and it interacts with the external magnetic field here. Then you have those which couple two magnetic moments, and then one has this term, which is the on-site coupling term, and this is, as we will see later, it's the one which is responsible for the electric field gradient. But you don't have to remember all these sets now, because we go those terms one by one. So for the chemical shift or chemical shielding, which is one of the most important NMR techniques or observables, one is looking at this term. So one looks how the external magnetic field interacts with the nuclear moment. And the chemical shielding, first it's defined as a tensor. So you know the tensors with a double overlap. So if you apply an external magnetic field and there's an induced magnetic field, then this ratio means a matrix tensor quantity, because you can have an anisotropic material. That's the chemical shielding. And in principle, you can derive it this way. So you have your total energy, the response, the first order response with respect to nuclear magnetic moment, and the external field. These are the Cartesian directions of beta, because it's a two-rank tensor, so you can write it also in this way. And then the observable, what is shown in the papers, that's the chemical shift. So that's related to the chemical sheathing by subtracting the chemical shielding of the material under study, the corresponding value in the reference. The reference is usually some well-chosen molecule where the signal is known. So this is a difference, and it's easier to measure experimentally, it's more reliable. And so this is the chemical shift you see in the literature. And in principle, this is still a tensor, and later, at least during the examples, we will discuss shortly how to interpret the tensor properties. Well, you saw in these equations, one has basically the first order derivative of the total energy with respect to magnetic field. Later we will discuss how this is done in practice. So here I just mentioned that one does this is the first order perturbation theory to get from the ground state wave functions to the first order wave functions. Then we get to the induced current using this one, and then the magnetic field. In the second part of the this talk, I will concentrate on how to get here to there, and when you have this, so then you get also the chemical shielding. Well, I mentioned that there's a second approach, especially because there's some authors in the audience and the organizers, to calculate, or the theory to calculate chemical shielding tensor. That's a so-called converse approach. And there one uses, if this was the method that I just described, so you take the chemical shielding, tensor element is the induced field derivative with respect to the external magnetic field. You can use the orbital magnetization, which is a quite new theory. And so if you take the derivative of the orbital microscopic orbital magnetization with respect to a microscopic localized magnetic dipole, here you also can get sigma. And this is a very new approach. So this is an alternative way how to get the chemical shielding. Well, I mentioned one property which is not often discussed in the literature, but it's very important when we have big samples like solid state. So it always has a surface, and if you imagine that you have a locally current, so in the induced current due to the magnetic field, like this, so this is the interior of the material, so you have the local currents. You have local currents all around each atom. This is now kind of two-dimensional representation of the crystal. So you have current around each atom. If you look at the surface, so if you have current this way, you have at the surface, you have a current which points always in the same direction. And so this gives rise to a macroscopic surface current. And it's actually important in the sense that the signal, what you obtain in the experiment, depends, if the material is anisotropic, it depends on the shape of the sample. So usually if one has big samples, so powder, for example, then it doesn't matter because you have all the orientations inside. But if it's well organized crystal, for example, you get this surface current, and then really the signal, the output of the experiment depends on the shape. So it's important to keep in mind, and I will mention it during the theory, what one has to do about this. Okay, the next term, or the next observable from experiments is the electric field gradient, and then one is looking at this term. So one has the interaction of nuclear spin at the same site, and one has this quadrupolar coupling tensor. So this is only observed when the nuclear magnetic moment is the electric field gradients. I saw here one. So one has defined again a tensor Q, which has two components, alpha, beta, which are directions. And then one has some prefactors. And then one has the expectation value of the electric field, one of these components, with respect to the Cartesian coordinate. And then you know this with the vector V. And here the EQ is the electric quadrupole moment. And that's something which is known and is taken from the literature. So you see that this value is just proportional to that value. And yeah, the E is the electric field in this case. And then when one has this tensor, usually one goes to the so-called principal axis systems. So one takes the eigenvectors, values of this tensor, and so the eigenvectors, they give you three directions, which are not necessary. They are orthogonal, but they're not aligned along the nuclear axis. And then the eigenvalues is something that you can measure from the experiments. And usually there's a convention that the eigenvalues, these three, the absolute values, are ordered like this. So first is Z, Y, Z6. So because now if you take the eigenvalues, there are of course only three components which are non-zero. So those are put in this order, and then the observables from the experiments. Well, the first one is the quadrupolar coupling constant. This one, which is again proportional to the same prefactor here, and then here's the largest eigenvalue of the tensor. So that's one observable. The other one is so-called asymmetry. I mean, one sometimes is two definitions with different sign, but basically that's just the difference of these two eigenvalues divided by the largest one, largest absolute value. So later we'll show some examples how one can obtain these values and compare the experiments. Then there's a third term which I will briefly introduce here. That's the so-called J coupling, so that couples the nuclear spins of two different nuclei. And of course, as you can imagine, if they have to couple the nuclear spins, they have to be pretty close in space, so that this element is non-zero. So this is the indirect nuclear spin coupling tensor. So in principle, one looks at the induced current, when one looks at nucleus I, one looks at the current which is induced by the electrons around the nucleus J, and this tells you how strong the coupling is. And of course, you can imagine that really as a function of the distance, it decays very fast, so you can get kind of a local mapping which nucleus is close to which one. So that's another technique. I'm not going to discuss it much in the rest of the talk, because that's not currently implemented in the quantum espresso code. So now I come to the GIPAW method. So that's the numerical implementation of this theory. So if you had, well, I showed it here. So you had the chemical shielding and the electric field gradient. So those are the two things that can be calculated using the GIPAW module in quantum espresso. And the GIPAW method is the numerical implementation. As you know, most of the applications of quantum espresso, they use pluripotentials, and that's where one needs this GIPAW technique. So we have again the chemical shielding. You saw this expression already. So you apply an external magnetic field and you have an induced field, you want to get this proportional constant. And you can get that using the so-called Biot-Savart law. So the induced field depends on the current. And here the one denotes the first order current. So if you apply a small field that induces a small change in the current, and then you have this vector product of this with the position. And just to mention, the c is the velocity of light, just a prefactor constant. So this expression, if you can calculate the current, you can get the induced field, because you have the external field, you can get the proportional constant. So now our task is to calculate the current, and I mean, there are some more or less straightforward ways how to do it in molecules, but we want to do it in condensed phase. So we want to study infinite systems like crystals or liquids, because we plan to use very boundary conditions, amorphous materials, and so on. So this creates a further complication. And then, as I mentioned just before, and you know it already, we use the pseudo-potential approach, and because this is a nuclear technique, so you are sensing the local electronic environment around the nuclei. One needs to reconstruct all electron properties around the nuclei. And we do it using the GIPAW method, and we'll later try to demonstrate that it's a really accurate method, although we use pseudo-potential.
In the Hamiltonian, you have three terms, basically three terms. What are the relative magnitudes of those three terms?
Well, it depends. So, for example, so this one is 0 for some nuclei, and then it depends on the, for example, the signal shape. In experiments, one measures or uses the signal, this oscillating magnetic field, in such a way that one probes only some of these. And usually this is the larger one compared to this one. Now is this is really for only some nuclei at the relative strength.
And the other point is, in the magnetostatics, the Biot-Savart is basically to find the magnetic field at a point due to arbitrary current distribution.
Yeah.
In this case, your current distribution, basically electrons are in the orbit and nucleus is in the center. How the Biot-Savart law here enters in the form of chemical shielding? How you picturize that Biot-Savart law is really working for the chemical shielding effect?
Well, I mean, the Biot-Savart is because it couples the induced magnetic field. If you have a magnetic field, the Biot-Savart law just gives you the local magnetic field.
That's fine, but how it is related to the effect of chemical shielding? What do you exactly mean? That this current or the dipole moment have a contribution in the chemical shielding?
Yeah, so I mean, I will go through it, and the derivation is quite long, and it's not so difficult, but it's quite long. I just mention and repeat this. So if we had the ground state here, then we apply the external field, and that perturbs the wave functions, and that induces a current, and then we use the Biot-Savart law. So it's kind of indirect. At the end, hopefully we will see that, okay, we get the proportionality. But so the magnetic field enters at this point. So you perturb the wave functions in the magnetic field. It's not straight in the sense, or the derivation is not that straight as just from here. You don't have it implicitly in the beginning. But I can guarantee that towards the end of the talk, hopefully we will see that we have this proportionality. And then, so the Biot-Savart is kind of just one step. We have to go through the orbital or the magnetic current. So if you don't see it later, please remind me again. So now coming to the famous gauge problem. I don't know, probably during the lectures of electrostatics you had in the courses, you have already encountered it. but I will quickly try to repeat it. So if you have a magnetic field interacting with your system, so this is the total Hamiltonian, so you add the momentum operator, the vector potential A, kinetic energy part, and then you have the potential. So this is not yet the density function theory principle, this is just the quantum making derivation. And we obtain the magnetic field, this quantity, and we have chosen this gauge now for the vector potential A. So if you translate your system, so we say that we shift all the coordinates with the position t, or it doesn't affect this one explicitly, but so this is the new Hamiltonian. But if you solve this system, you get the same eigenvalues as before, but the wave functions, they gain a phase which looks like this. So there's the translation. And in principle, your system, the results, the calculation, they should not depend on a translation. Of course, if you move your system by constant amount, there should be no effect. So this creates the gauge problem, and one has to cure the problem somehow, and the GIPAW method is the one that we are going to use now. And the GIPAW method, I mean, there were already, before this paper, there were already some derivations, for example, for properties in magnetic fields and so on. But this paper basically, for the first time, introduces the whole GIPAW method for calculating the nuclear shielding, or the chemical shifts, or chemical shielding. And you get, if you remember, you get the shifts just by subtracting the reference. So one adds something to the PAW method, which was, I think, introduced last week to you already, to take account or to cure this gauge problem. So that's the gauge, or the G here, gauge into PAW method. So the GIPAW is really kind of an extension of the original PAW method for the magnetic fields. And just to repeat those PAW equations, so if you were calculating your system using the pseudo wave function, so would you use it in Wave codes, then to get the all electron wave functions, you operate with this operator T on the pseudo wave function, and then you get the all electron properties. Well, the GIPAW method introduced something new. If you remember, if you would leave out these two terms, you would have the original PAW method, but now in the GIPAW you had at this point, you introduce these two, and these two terms in the operator T, that cures the gauge problem. So I'll go back shortly. So if you remember, there's this term, so you gain if you translate your system, and practically these terms, you see it's exactly the same term, that cancels the effect. So that cures these two factors, they cure the problem of the gauge dependence, or the position dependence in the gauge. And if you remember from the PAW, I think you were shown the way how to calculate observable. So if you have an operator, in this case arbitrary operator O, so if you do this transformation, you can derive that in the new value for this, the kind of all that corresponds to all electron observable is the one where you first operate directly on pseudo wave functions, and then you have this term. Well, you have horrible amount of these prefactors here again, but I can guarantee the final result is not that complicated. But what you see directly is you have like in PAW, you have the same, so the operator is between the all electron wave functions here, atom centered, all electron wave functions, and then you subtract the same contribution to the pseudo wave functions here. And that's of course around each ion core. But that's how you, in the PAW method, you construct it all electron properties. And here you do the same, but you have to take care of the gauge. So you get many times this gauge. Otherwise, the method is in principle the same. Yes?
How basically, pictorially, one should get a sort of feeling about the chemical setting? Is it when you apply the magnetic field, ground state is perturbed, so symmetry of the wave functions are little whatever disturbed.
Yeah.
As a result of that, the electrons in the valence states are sort of protected for further chemical reaction. Is it the meaning of chemical shielding? Sealed basically in short. That means you are, through the nuclear magnetic resonance, you are not allowing the electron to go for further covalence or electrovalent kind of bonding. Is it the shielding in that sense? What pictorially the shielding means here?
Well, I would call it more like a screening. I mean, like for electric field, if you apply an electric field, it replaces the electrons. I mean, it could become more reactive. The shielding in this sense, it's more like how the electrons surround. Then when you have the magnetic field, you displace the electrons, and then you change the shielding, and the shielding is...
shielding from what?
I mean,
for example, we know in case of helium atom, one electron sees the far electron is like a screening. Here the shielding is coming from this magnetic field, or?
No, the shielding is more like you have a nucleus and then you have electrons around it, so they shield it. An electron cloud around the nucleus. But it doesn't mean that it's shielding in the sense that it will shield it from reacting or so. It's just that there's something, property, or electrons are around the nucleus. And, then all what you are trying to do for the nucleus, in a sense, you have to take into account the electrons around the nucleus. Okay, so, I mean, it's not really preventing. And anyway, here we are looking at the response. It's in principle infinitely small for the base. So usually the strength of the magnetic field is not that large, even in the strongest magnets nowadays. So that one can use the linear response. Still get described.
Shielding is basically like a wall from the nucleus and the electron. So you are studying in isolation, one part putting a wall basically.
Well, it's not. I mean, I would just describe it the way that you have a nucleus and then you have an electron cloud around it. If you want to touch the nucleus, you have to discuss first with the electrons around it. It's not just protecting kind of thing. I mean, it's just that the electrons are around the nucleus. Well, for us, it's just a point. So to go to the nucleus, you have to go right to it. Are there other questions at this point? So
Ari.
So you said you don't include J couple?
No.
Isn't that a big deal, like the molecular?
Well, that's one observable. So usually the experiments, they really have chosen already, we want to look at this property, this property, or this property. So of course, we don't have it implemented now. It means that we cannot describe some of the experiments. And I agree that it's important for many applications, J-coupling. And I will describe, or I will mention, only recently appeared a paper which describes the corresponding method as this for chemical shielding, for J-coupling. But it's not yet implemented. It's more question of time than question of willingness. I think we don't think that it's important. Because that's really another observable, but that can help you to determine many things from the atomic nuclear structure, J coupling, which you don't necessarily see with the chemical sheathing. Okay, now we have this one. Then we try to go and see some of the. This is needed to go and describe the optical current we need for the chemical sheathing. We needed GIPAW to reconstruct. So first to get rid of the gauge problem, and then reconstruct all the two properties around the nuclei. And so I'm afraid the next transparency will be quite heavy. So lots of equations, and I'm not expecting you to understand them all, but we need to go through some of them just to understand the output of the code, because it gives you information about several terms, and already to understand what are the different terms, we have to go through some theory. So first, we have the magnetic field. So the bar above the letter now means that it's a GIPAW, Hamiltonian in this case. So we have the ground state, Hamiltonian, which is just that you don't have a magnetic field, and then we have the first order term. Then which one derives if one comes to this property. So there's the L dot P, normal term, and the non-local pseudopotential is the plane wave codes. We get an extra term, and this is only the nuclear position. So this is the per term Hamiltonian. Now we should get, this the non-local potential here, and this P is the so-called velocity operator. So now we have to calculate, we have the first order Hamiltonian, if you remember, that we have to get the first order wave functions. This you get with the debasement theory. So if you have the Hamiltonian here, you have the ground state wave function, then you have still the Green's function, which here the J goes over the virtual orbitals or the unoccupied orbitals, so you kind of project out the ground state virtual orbitals from the product of these. So you operate with the first Hamiltonian to your ground state wave functions, project out this part, and you get the further wave function. So that was the first thing what we need. The thing that we want to have next is the current. So remember the J, and we have to start from the real current operator. So if you have current operator J, then we write it in this way, where we have the paramagnetic current operator. In this sense, you have the P, the momentum, and then you have R, the position operator to the left, to the right, and then to the left, and then the opposite point here. And you can write it this way, or if you insert the gauge that we chose for the magnetic field, you can write it in either way. So we will continue now this way, because we want to have the B, and the B is now the external field. So in the following, I drop the subscript for the external field. Well, in GIPAW, if you remember what you have to do, you have operator. So what you have to do is you put it in here in 3 places, and you get the GIPAW value for the operator. So if you do that for the current, you will get quite a long expression. So this is the whole expression. So first you have here the term, so the pure operator, and then you have this reconstruction term. So you have here's the all-electron wave function. In between you have first part of the operator. You subtract this one, so it looks like a PAW transformation, and project this both sides. So this is just a definition for the change in the paramagnetic current to the reconstruction. And then you have the so-called diamagnetic reconstruction term, which is the second part. So when you insert it, when you insert this one to the expression for GIPAW for operators, you get this one. And this is the whole thing what you principle you need to calculate to get the current operator in GIPAW. So is this clear? So we have now the current operator that we need. I will show you shortly where you need it, more equations, but please believe me, it's not that difficult. So you have the current operator, and then you split it in the zero order term and the first order term. So if you remember, you want to get linear response, and you already did that for the Hamiltonian. So now we split those terms to things which depend on the first or the zeroth order of the magnetic field. And it's this one. This was just the definition that you had in the previous slide. And then you have the first order term. It just looks horrible, but you don't have to care about the details. So what's important now, we have the zero and first order current operators in GIPAW, and we want to get the first order current. You remember this was what we wanted, or by Savart law. So you take this operator, well, just three terms, because you have for the current expectation value, you have a wave function on the left, then the operator, and wave function on the right. Now we collect all those terms which give you the first order. So in this term, you take the first order here, so this has to be the zeroth order terms. You have 0, 0, first order, zeroth order, first order, zeroth order. So now you have the expectation value of the real current in the first order when you apply those operators. Wow. This was what we need for the magnetic shield. Well, then we regroup them again, and this is now more details that you don't need to know. But it says that the code really shows you three terms, or the chemical shielding for three terms, and those are the bare term, the paramagnetic term, and the diamagnetic term. And these are the so-called, or more like reconstruction terms. And this is just regrouping. If you insert this inside here, you will get these. I mean, it's not necessary to go through. Let's just take one example. So if you have here the J0 operator, you operate the first order wave functions, and first order wave function, if you remember, it was this object. And then you have JP and so on. And this is just regrouping, nothing special here. And you just get these three terms that we need later. Now I warn you already, more expressions. You have to know even less details. But if you reorder a little bit those terms that were shown before, and now we want to go for the infinite material, so solids, liquids, and so on, using varying boundary conditions, then we come to this kind of expressions which are basically local, but we have still operators like r minus r prime in that term, and the J delta P term we have r minus r prime. And this is still not yet something that we would have want to have in ferritic systems. So we use a trick, or tricks like magnetic mathematic equality. I'm not sure if I have everything exactly correct, but basically what you do is you replace r minus r prime with two terms where you have this phase factor minus the conjugate one, and then you take the the asymptotic limit when the length q goes to 0. So now we have introduced a property called q, which is it's in principle the length of the vector, but we want to go into 0. So if you would expand the Taylor series, so you would see that the first order term is just 1 minus 1, 0. So the next order term would be q times ul, and the argument. So if you divide it by 2I and the length of q, so that's independent of q. So that's the only term which survives because all the other terms are higher in q. So you basically get the same as this one. But we need to get rid of this, the GIPAW method, and let me repeat it again. So you have this, for example, here, amount up front here, and you get these kind of expressions where I will show you the value of S afterwards, but basically we use this trick for the two terms before. We have these horrible things, which I think I needed 2 months the first time to understand them. So you have all these Green's functions and so on. So of course you don't need to understand that. The important thing was what I wanted to show here was just where does this Q come from. So it's just a kind of mathematical trick to get rid of the differences in the real space. And after this, all the expressions can be used for extended systems. So they are localized in the sense that you can calculate everything in the supercell like before, and then you have this Q vector, which in principle goes to 0. When practice, it cannot go to 0 because if the Q is too small, you will get numerical difficulties. You know, Q here, and if you plug it in, put it too small, then you will get too small numbers, differences of very small numbers, you cannot calculate it. So there's kind of a numerical limit from below. And of course, because it's a limit, you cannot choose it too large. But usually the default value of Q, what is plugged in the code, it comes from a long experience of Francisco Maule and others, and that's usually a good value, a good compromise. Not too large, not too small. I just mentioned this. If you sometimes come to trouble, the results, you might want to check that the value of Q.
What is the generalized susceptibility kind of thing in this case? Like if you have any linear response, say regime, for every system there is a kind of generalized susceptibility.
And we can show you the susceptibility.
Before that, this Q is like 2 pi by lambda, right?
Yeah.
Wave vector, right?
Yeah.
What is the meaning of, like in solid state science, we have long wavelength approximation. What is exactly the meaning in this case, in these connotations? What is the meaning of Q? This is static limit, right? Somewhat.
Well,
Q tending to 0.
Yeah, it's a very
long wavelength.
Yeah.
What is that long wavelength here you have in mind? Wavelength of what?
I mean that you have the infinite system, so you have a really infinite system. So that is the limit that we want to go. The Q goes to 0. So we have an infinite crystal. And that
But for amorphous system, what will be that? Because this probe is also very powerful amorphous. You don't have any periodicity. You are lost.
Yeah, but with these methods and playmate codes, you always need the unit cell. So you need the maximum nowadays is 2,000 atoms that you can handle. We use periodic boundary conditions because that's more realistic than having just having an isolated system. So we always use periodicity in this case for the amorphous system. For surface or so on, you can think about. But for example, liquids, we always treat with periodic boundary conditions.
This capital S is like some kind of structure factor in this case? What S physically referred to? Like when you are going with the limit of Q goes to 0, you are measuring 1 by 2 Q is there, R at Q and R at minus Q.
Yeah.
What this S basically is a kind of structure factor of the system. What is that?
Well, it has kind of no physical curve in that sense. I mean, it's analogous to structure factor maybe, but it has no physical meaning.
Because I can see this is like any other spectroscopic technique, X-ray or neutrons. This is a kind of structure factor pattern.
Yeah.
You pick up.
But this is just a mathematical trick how to calculate those gamma and subprimes introduced in the Q.
Yeah,
So
but
it's not a physical
but
observation.
the idea is mathematical trick has to go with the physical system.
Yeah.
It should not be sort of
Yeah,
disintegrated.
Yeah, but I mean, by taking Q very small is the kind of limit that we approach when we go to very big systems. I mean, we are almost, if you could go to Q0, it's fully very existent. And, if the Q is small enough, then we approach the limit. So we numerically approach. So the horrible expressions, you don't have to remember this, but it was just to introduce the Q. And now we have the J. The first order, if you remember, had the expression, and we had 3 terms. And actually, for 2 of them, these are the so-called reconstruction terms, and they are due to GIPAW. We are reconstructing all electron properties, so they are local around the atom. Now we do the so-called on-site approximation. So instead of having the R local, that it goes through all the space, we directly say that, okay, we take this term at the position of the ion R. And then we have still this bare term, which is a delocalized term. And so there we cannot use this on-site approximation. So we first had to go, we had the Fourier transform this, that's a vector property. We Fourier transform that, and we get the induced magnetic field from the bare term. And that's for all the Q vectors not equal to 0. So when we have this, then we Fourier transform that into real space again. Sorry, this is just the Weierstrass law in G space, so using the reciprocal space. So we have this, and then this is done. So first you Fourier transform this into G space, so that the Weierstrass law looks very easy to calculate. And then you Fourier transform this back to real space, and what you get is here the induced field from the bare term, and then here you can do the same, so Weierstrass law, but now it's just on-site, so you don't need, it's just something at the atomic site. It's quite straightforward to calculate, and you can calculate those two also, the magnetic field. So now we have the induced field, and now again I put the external field, and now just going back to before, if you look at all those terms, so if you take, for example, J bare term, so yes, you see that it's proportional to the external magnetic field. And you have 3 components. Then you have 3 components for the way you observe. So that gives you the tensor. So you saw that all those properties in the induced field, what we calculated, they are proportional to the magnetic field. And so you have this proportionality and the proportional constant. Now we have it, it's the shielding tensor. So it was a very long derivation just to get expressions for the induced field, and it's always proportional to the B field, not external field. And then the proportional constant is the 2 times 2 or 2 tensor, 3 times 3 tensor because of anisotropy. There's one more thing, the susceptibility or the macroscopic term, which I shortly mentioned before, so the surface current. So from the previous expression, there you had, I mentioned that it will dissolve for all the terms except for the G0 term. And that has a physical meaning, that's the macroscopic term. So if you take G0, that's the kind of global value, macroscopic value. And that's related to the susceptibility. So actually, that would be the whole susceptibility, but it has to be consistent with the on-site approximation. One takes on the bare term or the susceptibility to the bare term, and one can calculate it using this. So one has 3 terms. Each of the terms is again this horrible property, but it's basically the side product of the calculation that you did for the current. So you can calculate the value for this also. And then you have the macroscopic susceptibility. So it's kind of a side product of the susceptibility. And as mentioned before, for the analysis, one has to take care of the shape of the crystal. So when we analyze the results, it's right there. We have to remember, or we can kind of plug in what is the shape of the crystal. There's a different term if it's isotropic or spherical. If it's
Why are you always considering the real part? Because in general, for solid, the susceptibility has both real and imaginary. Imaginary part basically gives rise to the absorption, and the real part goes for the refractive part.
Yeah.
In this case, you are putting real, you are only extracting the real part.
Yeah.
Why are you ignoring the imaginary part of the susceptibility?
Good question.
This is magnetic susceptibility, not electric susceptibility. Has nothing to do with the light absorption.
No, but if some of the magnetic field get trapped in the system, in general, susceptibility has both the structure.
The imaginary part is basically negligible for the magnetic susceptibility.
That's why I'm telling that how much negligible it is. How do you know that this is negligible?
Order of magnitude.
Because of V by C factor in the problem?
This is
First of all,
static
is it
limit,
zero
no?
frequency?
Zero
frequency.
frequency.
Maybe in high frequency imaginary part may be important.
No.
No important?
Electrons do not respond to high frequency magnetic fields. They don't follow. It's not like in the electric field case.
Because of this Lorentz force,
Yeah,
do not
it's much,
work
much
anything.
weaker.
Okay, that's the point. Okay.
Okay, so we had also the this can be compared to experiments. Then we reconstructed all electron properties for which correspond to valence electrons. So that's the PAW method. But we still don't have anything. We have reflected the core electrons for the chemical sheathing, and then it was in a paper by Franska Mauri and in this case Robert Kahn, Thomas Klöber, and they showed that basically independent of the chemical environment. So here are many different molecules. The core contribution to the chemical shielding is very close to a constant. I mean, it changes maybe this digit. Well, you will see later what is the order of magnitude of the changes in the valence part, but that can be hundreds. So this is 0.2. So basically, all these elements, all molecules, the changes are very small, even though the change in chemical environment is big. That's why what we usually do is we just add a constant term to the core electrons to the chemical sheathing intensity. So the PAW was to reconstruct all the electron part first with the valence electrons, then we add a constant to the atomic core.
In such high sensitive experiment, when that thing number is varying 198.8585, is it 2-digit sufficient to say the small change?
Why?
Because it's a high sensitive experiment. 4th, 5th digit should be a significant.
I will show it shortly in the applications part. You will see what is the order of magnitude for the observables. I mean, the numbers, the changes are really hundreds in some cases. It is. And then there's also the problem with the accuracy of the exchange correlation function, which is small. That, I mean, these are of course